for Duke Energy. So my team primarily focuses on really everything technical related to the identification, design, development, and execution of energy storage and microgrid projects. We also support kind of the commercial side of things. So we get kind of basically the details of both worlds there, the regulated side and the non-regulated side. So yeah, thanks for having me. I'll pass it over.
Thank you very much, Sherif.
Moemen.
Sherif is actually someone that is in a lot of our webinars, and he always adds so much value. So I'm getting a kick out of the fact that we have 4 hours of his time today. So please plummet him with questions. I mean, he's like a fountain of knowledge. Next, Mohamed, seriously, I will get it right, promise. If you could introduce yourself.
Yeah. Hello all. My name is Moemen Yassin. I'm working with Storlytics energy storage as an energy storage engineer with the storage modeling team. I used to develop some energy storage models for lithium and non-lithium energy. I have some years of experience in the battery modeling and the battery management system design. I'm very happy to be with you in this workshop, so you could benefit from what we are going to say and what cases we are going to illustrate with you. And yes, let's get started and see how it will go.
Excellent. And next, I'd like to ask Adam, please, to introduce yourself.
Great, thanks, Bailyn, and happy to be here today. My name is Adam Nygaard. I'm a director of business development at Flexgen. I'll admit that before I signed up for this webinar, I thought it was going to be 1 hour. So I'm going to throw a little shade at Sherif for then tricking me later into it being 4 hours. But I'm looking forward to it. Prior to joining Flexgen, I worked at Duke Energy for 13 years, and that's how I got to know Sherif. So when he did invite me to join this webinar, I did so, very willingly. But at Duke Energy, the last 5 years I was there was developing energy storage projects for the regulated utility, not the commercial unit that just sold to Brookfield. And then after that, I worked for a private equity firm. So I was there for about 18 months, and Frank was still there when I received this invitation. So I'll certainly be giving tidbits about Flexgen today, but I also threw on the vest to somewhat represent the kind of investment community and kind of come at this from the lens of an investor and how they think about returns and energy storage systems. So looking forward to the webinar today.
Excellent. Thank you very much. So there is a question, really good question which I was going to get to in terms of housekeeping, guys, now that you know the speakers today, and is that we are recording the session, so you're not going to have any issues. You can watch it again, you can share it with your colleagues, you can pass it around. And also one thing, we sent you an email where we told you that we will be using a software today. You could download it for free. So my colleague Christina is going to put the details in the chat in case that you need to still download it, you didn't get to it. It's just that way you really get your hands on it and you really are able to try for yourself and ask those questions when they come up. So I do recommend that you do it. Of course, it's up to you. And just one thing, I think, Sherif, you better be saying the point number 5 there. But yeah, pricing is illustrative, guys.
Yep. Yeah, I'll just echo that. So we wanted to make this as realistic as possible and go through the entire phase of project design. So obviously that involves kind of accounting for cost of different battery systems. So we just wanted to clarify here that the costs that are shown here, they're not related to any of the respective companies of the presenters. They're just for illustrative purposes.
Excellent. So now that you know that the recording is coming your way in a few days, you know that the materials are going to be available to you, that you're supposed to download the software if you'd like, and that you have the instructions. Just a reminder that to send your questions and that we expect them, because the point is that you ask the questions that you have, to use the Q&A box at the bottom of the screen, okay? And the chat is there, for what you are doing now. I love it, the roasting that we're doing here for the small print. So just keep on using it, and send your questions through the Q&A box, because they're so much easier for the speakers to manage, you know, when they're speaking and they're trying to get to them. So without further ado, I open I give the floor now. Mohamed, you're the first one to speak, correct? So the floor is yours.
Yeah.
And once again, please don't be shy and send your questions.
Hey, Bill, and I'll just go real quick through the agenda
okay.
first, and I'll pass it over to Moemen. So just to set the stage here, you know, we already went through the speaker intros there at the top, but after that, we wanted to really give the stage to Adam to put us in perspective of really why this workshop is important, right? So he's going to dig into kind of the financial aspects that you know, of developing projects. He's definitely got a wealth of experience there from, you know, his time at Duke Energy and now at Flexgen. So he's going to bring both that commercial and regulated knowledge to the table. And so after we do that and we're able to recognize why we're here, we're then going to go through the actual work, the actual design process to kind of address what we've identified as important factors. So that's what this second section is about. And through it, we really have three main optimizations that we're going to go over. So the first one is looking at, you know, what happens when you vary a battery usage profile. So when you take, you know, different types of cycles, how does that affect your design? The second optimization is looking at really the technology. So now if you know how your system needs to be dispatched and you have a usage profile, what is the best technology for you to use and how do you make that determination? And then finally, we'll go through kind of the very, very mundane question today of, all right, do we augment a project or do we design it to be an overbuild project? And what affects our decision there. So we're going to approach it kind of from a economical perspective in optimization 3. And then in section 3, kind of this one here, we're going to go over the risks of, or the risks and rewards of different augmentation and overbuild strategies. What do you need to know that is outside of the economical and financial realm that really will have an effect on your project? And then Adam and I will just bring it all in and just conclude and see what we took away from our time together. So with that, Adam, I'll pass it over to you for the first section here.
Yeah.
Why is this workshop important?
And yeah, and Sherif, feel free to chime in here too, right? Because you know why all this stuff's important given your experience. But you know, first I just want to reiterate that the economics that are shown here, we're going to show example IRRs. They're really meant to be illustrative, and they don't include, you know, we're going to mention maybe some specific vendors, but the pricing and economics really is meant to just be directional. So I wouldn't take any of them. I'll warn you up front, a lot of the returns, investment returns shown are probably going to look low. So I don't want to scare people off to think that battery investments aren't good, but just kind of want to throw that warning out there in the first place. So, you know, why is this webinar important? You know, Sherif, actually, if you don't mind, I would like to give a little bit of background on Flexgen before we dive into that. I know that that was at least kind of supposed to be part of the intro, because a lot of people that are on this webinar, maybe you're very familiar with Flexgen, or maybe you've never heard of us, but I do want to take just a quick elevator speech. It might be a long elevator ride, but if you'll bear with me. So Flexgen is, we are the energy management system or software controls for batteries. So really think of us as the Windows operating system for energy storage systems. And the Windows operating system analogy is a good one, because just like Windows works on HP, Lenovo, Dell, Flexgen's operating system, which we call Hybrid OS, works regardless of the battery OEM or the inverter OEM. And so that's kind of first and foremost who we are, and that's our main expertise. But in addition to that, we do three other things. And so the four things that we do are shown on this slide, which is the EMS that I just spoke to. Second, we do commissioning. So think of that as taking a project from mechanical completion to COD. We do that efficiently by doing any pre-testing and pre-commissioning and integration work at our innovation lab, which is in Durham, North Carolina, which is where Flexgen is headquartered. So if we haven't already installed our Flexgen hybrid OS software into a particular battery OEM and inverter OEM configuration, we do it in our lab there first to eliminate time in the field commissioning and iron out all the wrinkles there first. The third thing we do is what we call lifecycle services. Think of that as LTSA. So that's your performance guarantees. We do full wrap availability guarantees. We have a 24/7 remote operations center, which is adjacent to the lab in Durham, picture kind of shown here on the right. So that's preventive maintenance, spare part supply, warranty management, software warranty, typical sort of long-term service agreement, again, what we call lifecycle services. And then finally, if you need some access to equipment, some of our customers have access to batteries, they buy batteries themselves. Others use the terms and conditions that we already have pre-negotiated with CATL and or with SunGrow. We're able to buy product from really any vendors because, again, to the first point we made about our energy management system, we are hardware agnostic, but again, have ability to have short lead times and sort of pre-negotiated terms there. So just want to give a little bit of heads up of what Flexgen does, what we don't do. And Sherif, you can go to the next slide. We don't do EPC. We're not a construction company, and we don't tell the battery what to do. So you'll kind of see down here, we're not a trading algorithm or AKA kind of optimizer. But Flexgen is the most bankable energy management system on the market. We've received funding from Apollo and VTOL over the last couple of years. We've raised over 250 million from them. We have over 6,300 megawatt hours installed and under contract right now. And again, just to push through the point, we truly work with several different hardware providers, many shown on this slide: CATL, SunGrow, Samsung, SMA, and we're really the most flexible from not only a hardware perspective but a contracting perspective. So Sherif, appreciate you giving me a chance to kind of tell everybody who Flexgen is. We've got the website link there, and also happy to take any inbound through email if you're interested in learning more about Flexgen. So now, Sherif, we can talk more about what we're going to talk about. Why is this important? The main thing that we're covering today is really sizing, and it's sizing for both inverters and batteries. It's going to be mostly focused on batteries. And what we're showing here is sort of, okay, you go to your investment committee and you have to show your risks and consequences. And this is a pretty, rough deck. You would never go to, you would get left out of the room in your investment committee if you showed, a slide like this. But the point being, if you don't adequately size your PCS and project up front during even submitting the interconnection application, and then you realize it later on, you may trigger a material modification, get kicked out of the queue. You have to restart your entire project. That can be mitigated by adequate project design and sizing, which is what you're going to learn in this workshop today. Similarly, with best sizing, you could fail your offtake capacity test, either initially at COD or every year that you probably have to pass that test moving forward. There's several reasons for why that could occur, which we're going to go through in this webinar today, and make sure you have the tools and knowledge to either understand what risks you're taking or how to mitigate those risks and kind of deal with them appropriately. Sherif, what am I missing there? What else are we going to cover here?
Sure. So I can kind of explain this next one here. It's really in the same vein as what Adam just mentioned, right? A lot of things go into that sizing cell that Adam talked about, but one of them that I think is the most critical is degradation, right? So I think this is my most beloved curve that I didn't create myself, that I always reference, and it was created by Dr. Bulin Zhu from the University of Columbia. And what he did is he collected data from multiple projects that are performing multiple services in PJM, and simulated that in a lab environment for the same cell. So kind of took the same cell, ran it through different types of cycles that represent different services, and just basically plotted how these cells degrade with the same exact cycles. So just as an example, at basically 40, I want to say 4,300 cycles here, right? The same battery here that is in black, that was cycled from 100% down to 25%, had almost degraded down to, I want to say 77% or so, versus the orange one here, which was only cycled between 75 to 65%, but more times because it's a smaller depth of discharge. So to get an equivalent cycle, you have to do that more times. So overall, it's the same number of cycles, but with one kind of usage profile, you're down to about 94%, and the other, you're down to 77%. That's a big difference. Realizing that most battery OEMs will specify the end of life of their systems at around 70% or so. So it really makes a difference how you dispatch your battery system. So just for reference, right? If you look at a 10 megawatt 4-hour battery system, which approximately is a $20 million project, again, just illustrative numbers, this represents a $4.8 million error if you're designing the system up front and you assumed the orange and end up being the black, or vice versa. So this again underscores why kind of being knowledgeable about degradation, accurately simulating the cases that you have and how you expect to dispatch your battery is so important for project finances. The other point I'll touch on real quick is selection of the proper and the best fitted battery technology for your use case, right? I always like to say there is no such thing as a best battery. There is what is the most suitable battery, and what is the most suitable battery based on my specific use case. So what am I trying to do with it? So I think previously, since the evolution of grid-tied stationary battery systems, the method that developers have been following to select the battery technology has been mostly, all right, what's the cheapest battery with a performance guarantee we can get our hands on, right? And then, okay, that's what we're going to use, right? Versus, I think today developers are starting to get kind of more sophisticated on that aspect, and they're now finding that, all right, yeah, for this use case with a high cycling count, maybe we're better off with an equal hydrogen technology versus maybe this UPS application that really doesn't require any type of cycling and you're just going to charge the battery and leave it there. Maybe lead acid is going to be the best solution there, right? Because that's what lead acid does really, really good, just holding a battery charge, right? So understanding that piece and simulating performance of different battery technologies and their suitability for different use cases will really make or break your battery project. And so I'm going to go through a quick example here. So this is from an analysis that was performed by Moemen's company, Storlytics, comparing basically lithium iron phosphate to a nickel hydrogen battery that is gaining a lot of interest today called Venue. And the main question there was, all right, we know this battery is really, really good at degradation, this nickel hydrogen battery, right? It's rated for 30,000 cycles and guaranteed for 20,000 cycles. And as it executes these cycles, it doesn't degrade as quickly as lithium. But on the other hand, it's not as efficient as lithium, right? So, it is the higher, or is the lower round trip efficiency, low enough to really allow us to not care about the extra cycle life, or is the cycle life high enough to really offset the lower round trip efficiency? So that's what this analysis looked at, right? It looked at the full picture, calculated the net present value of energy losses throughout the lifetime of the project, forming a specific use case. In this case, it was 2.1 cycles a day, which is, it could be very fairly described as a heavy cycling application. So with that, what was found is, yeah, you're gonna, the cost of the energy losses are gonna be a lot compared to lithium, shown here in green. But really, since the cycle life is so high and the degradation you're going to get is so low, you don't really need to purchase as much battery as you would with lithium. So it actually offsets the cost of that, lower round trip efficiency. So now, instead of spending about, 75-ish $1 million on lithium, you're at around $59 million with kind of a more optimal solution, basically taking into account the capital and also O&M. So this is why this is important. And I think that was our last one. Adam, anything to add?
No, we're going to go into this in more detail in the optimization, I think number 2, right? So
Yep.
No, you hit it spot on. And just to kind of one more thing about the use case, a lot of times I would just say when we have customers come to us and they just say, oh, well, we need 100 megawatt hours for 20 years. And there really is no other details into the battery, like how the battery is actually going to be used. And maybe the customer doesn't know, that's probably fair. But we're going to show you how that can really impact, if you did have that level of information, how that can really impact the sizing. And then again, help us, Flexgen, when you're trying to choose the right hardware, we can help you with that, as well as kind of in coordination with Storlytics and their expertise around the batteries to really make sure you select the right hardware to meet that need. So anyways, yeah, back over to you, Sherif or Moemen.
Yeah.
Great.
Moemen,
I'll pass it over to you. Go ahead.
Yep. Thanks, Sherif. Thanks, Adam. And now I'm gonna show you in this section how you can start designing your energy storage project. But before I can dive into this section, I think all of the participants received an email of the instructions to download and just set up Storlytics on your machine. So I think if you can just set up and open Storlytics along with me during this section, I think you will get the most benefit. So you can follow up step by step. So if anyone have any question about setting up Storlytics, I think he can put his question in the chat or the QA section. Okay, let's start with our project performance requirements. So we selected certain performance requirements for all the design cases that Sherif and Adam will go through in this workshop. The first requirement is the power requirement at the point of interconnection with the grid, which is 100 megawatt. The duration of this power to be 4 hours. And we have an end of life dischargeable energy at the point of interconnection with the grid to be 400 megawatt hour, which means that your system must be capable of discharging this amount of energy throughout the project lifetime at any year. The last requirement we have set is the project life, where we gonna simulate our system for 20 years. Okay, now you have known your performance requirements, and what is missing now is just to start designing your system to meet this requirement. And in order to start designing your system, I think a very important input must be added as a designer, which is the battery usage profile, which simulates the operational characteristics of the battery that your point of interconnection will behave with when you are connecting your energy storage system with the grid. So our software, if you just like tried to run any example or followed any video on the YouTube on our channel, so you can be familiar of how Storlytics is providing a very, very powerful module, which is a battery profile creator, which we will gonna use in the next slide to start designing our battery usage profile, because it really differs, like Sherif described later. So if you are a designer now and you want to design an energy storage project, so it will be very, very helpful if you can just settle down on your application and your cycle types and your just all the electrical requirements you need in your project. So let's get started with developing the battery usage profile. So I picked an application just to illustrate to you how you can use the profile creator, which is the energy arbitrage. So now we have the requirements we mentioned before, which are the power 100 megawatts, the duration is 4 hours, and the round trip efficiency here is to take in as 92%. So step one, if you open Storlytics window, you will see the battery profile creator. You can start with the first section, which is the application selection. Storlytics right now, in the current version, we have 3 main applications: the schedule and the peak load shaving and the clipped energy storage. So I expect the schedule application where we are gonna simulate the application now, the energy arbitrage, but still you have the ability to select 2 or more applications, and there is a good option in Storlytics you can use, which is the mode application priority, which is step 2. You can use among of priority or stack. You can just stack your your applications, like what will appear to you in the app priority window, or prioritize your applications with the order you want, just during the simulation of your project. So the third step will be the profile settings. You have to just mention to the software the number of days and the time step. You will simulate or just output the battery usage profile, your usage profile up to 1 year, and the time step is down till 15 seconds. Then we will just jump to the application details. I think there is something. Yep, here we go. So the application details here, we will go to the tab of the application selected, which is the schedule. You have to just input the parameters needed for the discharging and the charging tabs, where you can specify the power at which you want the battery system to discharge and to charge. So you can select the starting time and the ending time for discharging, and the same goes for the charging. And in Storlytics, we have the capability of selecting several months, where you can simulate several season conditions for your energy storage system. After you can add that as an input. So, okay, next. Okay. So the last thing we have now in our steps is defining your user definitions, where you have 2 main inputs here. The first one, which can limit your discharge and the charge during the project. So let me clarify this point. If you have now 3 different applications, maybe schedule and peak load shaving, and you want to simulate your project that will serve these 2 applications, so you can set limits for the discharge and the charge throughout like the project, we don't need this option, right, in our cases. But I think it will be very helpful for you if you are going to simulate several projects. So the second step after that will be equalizing the energy, daily charge and discharge. And here I just want to stop and just illustrate it step by step. Why we need the energy equalization in our project. So I think we know all that no battery is efficient 100%. So if you want just to discharge for 100 megawatt hour during a day, that not means that you want just to charge for 100 megawatt hour a day. There is a losses, and the efficiency for the battery itself must be taken into consideration. And here we are assuming auxiliary loads of no auxiliary loads in our cases. So we set the round trip efficiency with 92, which means that, okay, you have now 400 megawatts to discharge, okay, but that means you, with the time window, you will specify inside this section, the daily starting hour and daily ending hour. You specify certain time window just to equalize your battery with the certain amount of the energy that's needed to be charged to the battery according to the number of the round trip efficiency that you will set. I think it will clear now, and if you just need to understand that more, you can run like different projects with equalization and without equalization, and you can see the difference. Okay.
Yeah, and I'll just add here, kind of as you shift to like running an actual simulation with like an actual battery system defined, if you're not accounting for round trip efficiency, and if you have basically, if you're not energy neutral, or at least close to energy neutrality with a shift towards more charging, what you're going to find is that if you have a multiple day simulation, right, is that day over day, you're either adding on more charge or adding on more discharge if you're not energy neutral. So if you're running a year, you'll find that maybe like in January, your state of charge keeps on going up until, you know, it hits kind of the upper ceiling of the state of charge range, and really the results really don't make much sense. So that's why it's important to account for round trip efficiency and make sure that on a daily basis that you're equalizing and neutralizing energy with round trip efficiency in mind.
Yeah, thanks, Sherif. Thanks, Sherif, for stating this point. Perfect. Thank you. Okay. So now, after you settle down all the parameters you needed for your application, you can easily generate the report using the Storlytics. So the first thing you will see inside the report is the overall profile view of the 24-hour profile. So it's clear now that we are charging with 100 megawatts for 4 hours and discharging the same. But I think then the slide next that will just clarify more the energy equalization and how. Yep, here we go. So you can see now after we settled the starting hour and the ending hour for the equalization, okay, the battery now is charging with I think around 230. 230 maybe during this time frame, just according to the equalization round trip efficiency we mentioned before. So yeah, another output from our report is the power set points distribution, and this is a very helpful histogram to tell the designer of what amount of power his energy storage system, the power level is operating at. So you can see we have two axes here, the percentage and the count. So the percentage describes the percentage of the power value all of the time that the energy storage is operating at. Like the third bar, we have power from 3,000 kilowatts up to 4,300 and 200, maybe up to 4,000. For what percentage? For, I think, more than 70%. So, which means that higher power levels are operating just less than the other ones. The same goes for the energy. So, yep, this this graph tells us the same thing. So you can see on daily basis. So if you're simulating 30 days, so you will get a histogram of what energy level at each day you are operating your energy storage system the most. So I think that could tell the designer, okay, he can neglect maybe some values or just compromise with the design he is performing according to this graph.
Yeah, and I'll just add, I think this is really helpful to kind of allow engineers and business development managers to be able to recognize when there's diminishing returns on energy capacity of their systems. So, like for instance here, if you know that you're getting about 80% of the discharge days with I want to say about 54 megawatt hours, you can then decide, all right, is it really worth that additional 10 megawatt hours just to get the last 20%? So really, the more horizontal this cumulative distribution function is, I think the more opportunity you have as a designer to really neglect, adding battery capacity that's not really going to be utilized much for the use case. So I was using this charging panel or discharging panel for this example, but it also applies to charging as well, right? You want to recognize when you start getting diminishing returns and design based on that inflection point, if there is one. Same goes for power for sizing your inverters, right? I mean, inverters aren't as expensive as batteries, but still, right? In this example here, I mean, you're basically doubling your power capacity for about a 23% addition to the number of power set points that you're capturing. So really, it helps you kind of make that determination. And at the end, it depends on the use case. Maybe you have to design based on the 100th percentile for your use case. But if not, then you kind of have that analytics to help you out.
Yeah.
All right. Anything else, Moemen, on your end?
No, thanks. Thanks, Sherif.
Hi, Moemen. There are a couple of questions for you in the Q&A. Just to give you a couple of them, there's a lot of interest in the auxiliary load, for example. They're talking about why the auxiliary load is not considered under step 7. I don't know if you can give a little bit more of information about downloading and the different steps again.
Okay, let me see the question.
It's the last one. Let me send it to you.
Okay, the question for the auxiliary load. It's just we neglected the auxiliary load in this case, so we can like not have a complicated sizing problem. So we can facilitate the battery profile creator. So just for easier analysis and just not going into details or complexity.
Yeah, and I'll just expand on that a bit. When we were kind of preparing for this workshop, among the three of us, we discussed that we really want to focus on, the battery side of things, right? Auxiliary load for lithium is considerable. I mean, with auxiliary load, you're looking at probably, if you have a 1 cycle a day application, your round trip efficiency would be around 85% or so. But as you kind of correctly identified, the 92% round trip efficiency there implies that we're basically just focused on the cable losses, transformer losses, the battery internal resistance losses, without any of the auxiliary load. So it'll become more clear when we get into the more detailed modeling under the battery system modeler. But yes, you're right. We are neglecting auxiliary load for just because we want to focus on the batteries. Good question.
Okay. Great. Well, thank you. Well, for the sake of time, Sherif, if it works for you, I think Moemen will give you some time to check the questions while you move to the next step, which is optimization cycle type variants. And then I'll let you know when we have questions coming your way as well.
Cool.
Okay. All right. So optimization 1. So as we discussed when we went over the agenda, right? The first thing we're going to focus on is the type of cycles, right? If you have two exactly similar projects, one of them is running really, really deep charges going from 90% down to 5% or to 10%, and the other is just hovering around 50% or so state of charge, while kind of executing the same number of equivalent cycles per day. So both are 1 cycle a day applications. How different degradation do you get? And based on that, how much different does your overbuild capacity or your beginning of life capacity need to be? So, let's not forget the quote of a wise man who said, not all cycles are created equal. We just know someone said that. We don't know who that is, but, it's true. Trust me. So let's get into the details here. So in this first section, we're basically setting the usage profile in the simulation. So we're basically using the one Moemen went over in the first section from the battery profile creator. So now that we have this, we basically just input that into the POI profile input as a CSV. And we basically have 3 exactly similar days that we're simulating. All of them looking like this. You're charging in the morning and then discharging later in the evening here. So we specify that BESS profile, and then we start kind of filling out the equipment models here. So here we're assuming a LFP battery, in this case, CATL's 280 amp hour cell. And the inverter model we're using here, folks might be familiar with it, is the Sunny Central Storage 4600 kVA unit. Then what we're doing is we're simply kind of varying or basically sizing the system, keeping an eye on the sizing assist tool here. So if you're following along, on your own, what you want to do is click calculate energy and power required. That way, the maximum discharge and charge powers will show up in addition to the maximum energy that's discharged per day and maximum energy charged per day. So as you change these values, you put in the number of battery modules per rack, the number of battery racks per inverter, the number of inverters, and the losses you're assuming for the medium voltage transformer. And if you want to include the GSU, you can do that here as well. But as we alluded to earlier with the question around aux load, it is correct. We are assuming 0 aux load here, just kind of for simplicity. So then you start to set your kind of operational limits for your system. And one of the things I wanted to touch on that you really learn through operation is that the burden of energy management between battery racks that are placed in parallel is very sophisticated. It is not currently in the industry, it is not 100% figured out. That's why with I think with all LFP cells out there, it is very difficult to kind of get the full range of that SOC range, unless you literally just performed a balancing cycle, which differ from one OEM to the other. So that's why really in the design process, you want to account for that, smaller depth of discharge that you have access to in your battery. So here, we're being a little bit optimistic with 93% and 3%. In reality, this would probably be more around 90%, and this would probably be 10% for most LFP batteries out there. And then here, kind of set your assumptions on battery degradation. So we're assuming we're starting off with new batteries represented by the 100% state of health here. And as we mentioned in the project requirements section, we're assuming a 20-year project life. So after we run that case, this is what we get. I think the output we really wanted to focus on here was that, okay, the system we designed fully meets the requirement of the use case at year 0. So what you see in this radar chart is basically the charge and discharge at different points on the project. And what you see here in blue is the power capacity, and in orange is the energy capacity. So in other words, what percentage of the power set points and the energy set points was achieved? In case of energy, it's kind of daily throughput, basically. So if you look at all the charge throughput signal at the point of interconnect, and you want to see how many of those were achieved, you get that percentage for basically the orange here. So what this is telling me right now is that 100% of the charge set points at the point of interconnect was achieved, right? And at the inverter, the battery, and so on. And for the discharge as well, 100% of the discharge set points were achieved for both power and energy. So long story short, the system sizing is adequate. Now, where we start running into issues here is all right, we're designing this project to be a 20-year life, but we're finding that it's actually degrading down to 273 megawatt hours, which means we're really not meeting the requirements of the use case, which is maintain at least 400 megawatt hours at the point of interconnect by year 20. So then kind of, to solve this, we need to add more capacity. So what we basically do is we start adding battery racks to the design. So before this was, I think it was 64, where is it here? Yeah, it was 64 racks per inverter. So we increased that to 91 racks per inverter. So we check kind of the output or the energy adequacy and power adequacy as well. We're still good, 100%. And what we find here is that, all right, now we have more than 400 megawatt hours at the battery terminals. Also, the state of health here is 66.8%. You will find some battery OEMs, specifically LFP battery OEMs, that allow their cells to degrade down to 65% and will give you a performance guarantee at that level. So really throughout all simulations here, we're assuming the minimum state of health or the end of life state of health is 65%.
Sherif, quick question that just came up. Where did you get the degradation model from? Any scientific publication? And how precise are the models in this regard?
Sure. So the great thing about this tool is that it allows you to input the model details, get to the equipment model. So if you click this button, it'll open up, you'll see a bunch of parameters. So there's really a lot of ways to get that. You can either have the battery OEM fill out these fields for you because really they know their system the best. You can rely on a third-party laboratory to do that. But I think from the maybe
I can help with that. Yep, I can help with that. Okay, so it's very, very good question. Okay, the models we have in our software are validated in several laboratories, and we developed the model like using the OEM data sheets and like certified information from them to develop our models, and just to we have a generic models in our software, and for example, Innervini's model was developed based on the data given from them to us. So we developed our model and just validated that in their laboratory and got the results. That's why we issued a lot of battery models with this way. So go ahead, Sherif.
We've gotten kind of validation reports from Moemen. I think they did a great job with that, kind of really comparing the test results to what the model produces. So I think you can, for those validation reports, you can reach out to Moemen for that, right, Moemen?
Yeah, thank you.
All right. Yeah, great question. Should we take any more? Is there a charge discharge?
Sure. There's another one from Wes Bolson about this section that says, do the system rule out certain battery technologies, such as Leon, when the user types in the desire for something like 100 hours of storage, 1 gigawatt, 10 megawatt system? I don't know if you might need a bit of clarification there.
No, I think I get what's being proposed. So really what will happen is if you input something that's really, really off in here, like you have 1,200 modules in series, and that's equating to 100 kilovolts. When you click run, you'll get a message saying that no, your rack voltage is not matching kind of your inverter DC input voltage, and similarly, if you surpass the short circuit threshold of the inverter, you'll also get a message saying, no, the number of modules for this specific, or number of racks rather, for this specific inverter is creating too much short circuit current that, makes this really simulation inaccurate. So you have to kind of put in a reasonable design.
Yeah, and I can maybe ask a question here too. This is probably for Moemen. At Flexgen, our application engineering team does really a job of really knowing whether a certain configuration is even physically possible, because our software has to integrate with those hardware components, right? So I guess my question to Moemen would be, does the model here with Storlytics actually take into account really like constructability, which maybe Sherif just kind of talked to a little bit, but I think Moemen might be best to answer that.
Yep, sure. It's taking into account that.
Yeah, and there's also, I'll mention there's a lot of custom solutions out there. I mean, the example that Wes mentioned is really, really out there. Has 10 megawatts, 1 gigawatt hour, so it's like 100-hour system. So yeah, I definitely haven't seen anything like that. But what you probably need to account for is that there are custom solutions out there. It's not just about what the inverter OEM is doing, but also there are a lot of battery integrators out there that put together really sophisticated fusing schemes to allow higher duration systems. Definitely not anywhere near the 100-hour duration system you have here, but more kind of like when you start getting into 6-hour, 8-hour and beyond, you start getting into like a need for more sophisticated systems, especially if your inverter has a common DC bus. So there's a lot of inverters out there that are basically multiple inverters within a single inverter. So they have multiple DC buses. So that makes life easier in a way, but they are, in most cases, more expensive on $1 per kW standpoint. So kind of pick your poison. So, all right, but really, really good question. Thanks, Wes, for that. Okay. So we concluded the deep discharge case, right? And we achieved, accomplished the mission of sizing the system. Now we want to switch basically to the shallow discharge case, right? So we're basically going to take the exact same project file that we developed for the deep discharge case, and now just input a different battery usage profile. So in this case, this is basically a frequency regulation market signal. I think it was from PJM. I may be mistaken on that, but it has exactly the same number of equivalent cycles per day as the first case. So when you look at the two, right, it's 1 cycle a day here and 1 cycle a day here. Only difference is, the first case, it's deep discharges, and the second case, it's more shallow discharges, which you would expect from a frequency regulation use case or ancillary service. So we're not going to go through the exact same steps as we did on the first run, but with the design that was put together, it achieved the requirements of the use case. We found that similarly degraded down to less than the needed capacity, which we set as 400 megawatt hours at the point of interconnect. So now we're kind of going back and adding additional racks to be able to maintain that 400 megawatt hours for 20 years. So we achieved that here, and what allowed us to achieve that is 548 megawatt hours capacity. So you can see that it's quite different than the first case. I think it'll become clearer here in the comparison slide. So Adam, I'll pass it over to you here to kind of go through that comparison.
Yeah, great, thanks. And again, just to set the stage, the whole premise here is that you as the product developer and owner, you own this battery project, but you've entered into an offtake agreement, typically called a toll agreement, where you don't have control as to what the battery is told to do. The off-taking utility is making that call. And so you've entered into the assumption here is you've entered into a 20-year fixed price toll agreement with no escalation. You've operated it well over those 20 years. You're not receiving any penalties, and assume just a $15 per kilowatt month revenue stream. For CapEx, we're assuming some fixed acquisition, development, land, and owner costs. We would say that these are not ITC eligible. Again, don't take any of this necessarily to the bank, right? This is for illustrative purposes, but we've assumed a $6.4 million number there. And then breaking down really the equipment and EPC costs, we broke them into really just three categories: BESS supply, inverter supply, or PCS supply, and then lumped in EPC, balance of plant, EMS, and commissioning all in one. And you can see the values that we've sort of assigned to those. All in all, you'll see we're kind of approximately a little over, I think it's $300 per kilowatt hour, which you'll see in the next slide, which is pretty close to being in line with, I think, what you'll see kind of NREL publish or maybe WoodMac. If you can go back just real quick, I want to cover a few of the other assumptions though. So, some other things, because we just talked about these two different sizes that Sherif went through, right? One's 700 plus megawatt hours to meet the requirement, the other's 500 some. The change in size isn't just CapEx. It doesn't just have an impact on CapEx. That one's pretty obvious. It also has an impact on all of these OpEx items. So LTSA, that's typically going to be dependent upon the number of batteries you have at your site that need to be maintained. Maybe that's obvious, but obviously, if you have a larger number of batteries installed, kilowatt hours, then those LTSA costs are going to go up. BESS extended warranty, similarly, very directly attributable to just the battery portion that's being installed. And then other assumptions for expenses are inverter extended warranty, insurance, property tax. We don't have any costs assumed for qualified scheduling entity, because in this case, the off-taker would qualify as that and be that entity. And then also some other things as well. So tried to kind of keep it simple, but also at least complicated enough to show directionally how a change in the usage profile here impacts returns. Another, just briefly touch on the investment tax credit. We are assuming a 30% ITC here. It's paid the month after COD. That they just actually released the transferability guidance, which also impacts direct pay yesterday, I guess. And so for those that maybe follow me on LinkedIn, I did just add there's a link to a webinar hosted by our friends at McDermott, Will, and Emery. Carl Fleming over there is fantastic. They're having a webinar tomorrow to dive into that in more detail. But the point there is they're probably, you're probably not getting the full 30% there. There's probably some sort of discount, right, for transferring that credit. But again, just want to elaborate on the assumption made here. And then finally, project life. We're assuming the project ends basically the same time as the toll agreement or contract. So we're not assuming any terminal value. We're not assuming any residual value, aka kind of salvage value, or assuming that there's any cost to decommission the site. So now let's take a look at the kind of financial comparisons between the two, right?
Adam, sorry to cut you.
Yeah.
There's just a question. Just if you could
Sure.
explain a little bit what our EMS cost. One of our
What is EMS cost? That's the energy management system. So that's that's actually what Flexgen provides. And so there's an upfront capital component of that, which is the servers and the software, and then there's typically an ongoing component of that for continuous software upgrades and service, which is typically part of an LTSA, or at least with Flexgen, it would be part of an LTSA. If that can be different depending on who your partners are.
Thanks for the clarification.
Yeah, absolutely. There we go. Yeah, thanks, Sherif. So performance requirements, right? Sherif, we just covered all these. They're the same for each situation. And in this case, again, we're assuming no augmentation. Whatever you install in year 0 gets you through the entire 20-year life. Not the typical way to design a project, by the way, right? But here's the results. And they're kind of stunning, to be honest. So a deep discharge, you literally, as Sherif and Moemen went through, would need to install 712 megawatt hours initially to meet the requirement. And we saw that the limiting factor there was really more about that 65% state of health rather than the 400 megawatt hour limitation. And another piece of that being the depth of discharge. When you do those deep cycles, you really only have access to 90%. Whereas, in the shallow discharge example, so looking at the blue, 547 megawatt hours, that's a pretty dramatic decrease in initial upfront oversize. So what does this mean? This means that your upfront CapEx is a difference of approximately $45 million, the 220 compared to the 173. Additionally, you see savings on the OpEx side because of that smaller, less cells to maintain and service throughout that lifetime. And so what this looks like from a return perspective, and we have it shown both with and without ITC. We did that because I think we do have quite a few international folks on the call, so you may not care about our 30% ITC here in the US. But these are unlevered pre-tax IRRs. And want to point that out as well. So, quite an impact of, over 300 basis points in your investment returns for assuming that. So how do you think about this as an investor, right? You probably assumed the deep discharge cycle when you were running this case. You probably didn't think about shallow, and that's probably like the least risk averse approach, right? Because that's the worst case scenario. The worst case scenario is your off-taker doing the deep discharge cycles every single day, 365 for 20 years. That's what we've assumed here. And so you wouldn't build your project to the shallow discharge, but at least now you have a sense of, hey, do I want to size this maybe somewhere in the middle, take a little bit of risk that I'm going to have to augment later on down the road if I don't hit it because the worst case did happen. You have to have that sort of sensitivity and information. This gives you the information of what is really more of a best case scenario versus a worst case scenario from a usage standpoint. So hopefully that's helpful in shedding some light on the difference between deep discharge and shallow discharge. Sherif, what else? We talked about this a lot as we were kind of pulling this webinar together. I feel like we had more back and forth on the discussion here. What other points am I missing here?
Yeah, I think one of the things we discussed that I wanted to kind of mention here to the wider group is really we're at a point where there's a lot of players in the industry that believe it's really enough to say 1 cycle per day, right? Yeah, just design us a battery that is going to be dispatched 1 cycle a day, right? As we've proven here, that's not enough, right? And I think the only way the industry will advance is kind of if developers kind of start really asking the questions, right? When you say 1 cycle a day, right? How are you going to use this battery, right? Because I'm putting a lot on the line here. I'm designing the system, right? So is it going to be a deep discharge? Can you give me a battery profile? Because I mean, at the end of the day, right, when you go out and probably all the developers on this workshop are going to be very familiar with this process. When you go out and you're purchasing the battery system, right, you're talking to Samsung CATL or any of the new integrators, the first thing they're going to ask you is, can you give me a battery usage profile? How are you going to use this battery, right? And then they're going to give you a performance guarantee. Some of them have their kind of standard, off the shelf, 1 cycle a day. In that case, they're assuming the worst case scenario. But in a lot of cases, they will say, give me a usage profile and I'll tell you exactly how much battery you need to purchase from me, right? For this project to last 10, 15, or 20 years based on what you want, right? So I think that sophistication needs to kind of expand in the industry. And I think it's going to come from developers competing and wanting to put together more cost-effective, reliable, and minimal risk projects. So
yeah, agree. And kind of to that point, just to elaborate, right? Because this is kind of assuming a toll agreement, and there's probably a ton of people on this call that, hey, I'm only doing merchant projects, and maybe I'm doing merchant projects in Texas. Well, all of this still kind of applies. You just may not have like any kind of liquidated damages if you don't actually meet this requirement, right? There maybe is no requirement, but you're trying to optimize your project to maximize revenues in that merchant market. Well, you still want to make some sort of assumption. Hey, maybe the first 3 years you're doing just ancillary services or kind of the shallow discharges. And then maybe you want to be more conservative and assume kind of from years 4 to 10, you're doing energy arbitrage, or maybe it's some kind of combo of the two. If you kind of take that next step of going to that level of sophistication, you can really optimize the size and optimize returns.
Yep. No, absolutely. And I think one point that it's interesting to me, probably most of the folks here on the, attending this workshop are probably familiar with solar and what goes into the design of solar facilities. We get really, really accurate around production estimates for energy. You calculate your levelized cost of energy, and you're probably now with the tools that are out there, you're within 2% accuracy or so. And that's solar, where we're talking about PV modules that are 30 cents a watt, even cheaper or so, or it's probably cheaper now. So when you look at kind of now the cost of battery cells on $1 per kWh perspective, you start to realize that, we should actually be focusing more on modeling battery systems than solar, because it's just so much more expensive. I'll just shift here quick to some questions we received some really, really good ones. So the first one here: how do lithium-ion batteries compare to redox flow batteries for O&M? This is not really covered within the workshop, but I'll just kind of relay my experience, and I'll kind of pose that to Adam and Moemen as well. But really, I think the primary impediment that's been there with flow systems has been reliability of operation and O&M. And I like that whoever asked the question, Mesmer, here, he or she are focusing on O&M, because there is a lot of maintenance required for flow systems. It's a mechanical system. There's pumps, that you have to maintain, but that's one side of it. The other side of it is the round trip efficiency. Since whenever there's a mechanical unit in the system, you start to get really much lower efficiencies. So you have to kind of account for that. And really for all battery systems, something to make sure you're aware of is efficiency is not constant, right? When we say, lithium round trip efficiency is 85%, that's a really, really general statement. It could be much, much worse if you're just keeping the battery there and not cycling it. So it's important if you're interested in a comparison between two different technologies like lithium and flow to model both and see for your specific use case which one makes sense. Because I mean, for a low round trip efficiency system, right, maybe a low cycling application will make it more attractive because you're not losing as much energy, right? So really depends on the use case. And that's what we're going to find in optimization 2 here. We're going to compare two different battery technologies and kind of expand on how we uncover the differences there. Adam, anything to add on that, or Moemen?
I don't, Sherif. I can honestly just say I don't really have experience with what I would say is a kind of a real flow battery at this point. So, yep.
All right. Moemen, anything on your end?
No.
All right, so we'll take the next one here. Are the profiles of renewables and customer loads provided by the utility, or Storlytics develops this information? Yeah, I'll take that one real quick. So really the profiles we're using here, they're kind of just for illustrative purposes, but the source of these profiles really depend on your entity. If you are the utility, right, and you're designing this system for like to defer a substation upgrade or to provide backup power to like a town that has poor reliability, so then you can pull these profiles yourself. You can get the load of the feeder you're targeting for asset upgrade deferral. But if you're kind of participating in a merchant market, or if you're participating in PJM or some other ISO, then you can look at historical data for the service you're planning to participate in. So for the shallow discharge case, we actually use the PJM signal for frequency regulation from the Reg D signal. So if you're in that environment, that's where you can get it. So really, to answer the question clearly here, it depends. Are you the utility, or are you a developer, or where exactly are you in the supply chain there? All right. I'll just take one more question, and then we'll just move on to the next optimization.
And we can leave the questions for later on.
Yep.
Sure.
All right, so RTE is seen in the AC side or DC side, and it is included the auxiliary services consumption or not. So I think we alluded to this a bit earlier, but auxiliary load here we're assuming is 0. And for lithium systems, auxiliary load is mostly HVAC. I want to say probably 99.5% of auxiliary load is lithium. Is HVAC load for cooling and heating the battery cells. The last 0.5%, that's just control load. So here for this comparison, since we're just comparing two cases, we're leaving HVAC load out of the equation right now, and comparing based on everything else. But losses within the system, like copper losses, core losses within transformers, that is included here.
I can add a quick update for our next version. This is regarding our software. So in our next version, we will have enclosure models that will simulate the allow the user to simulate different auxiliary loads. So you could be able just to define your enclosure model, your enclosure type, or the adding to that the TMI profile, which allow the user to input the current temperature, ambient temperature of the site that the energy storage system will be installed in. Yep, here Sherif, the TMI profile. So using this profile and the enclosure models that will be added in our next version, and sure the battery sizes will be helpful in the giving some insights of the auxiliary load consumption based on the selected enclosure file. So just a quick update for that will be included in our next version, for more accurate results in the analysis.
Great, thanks for that addition, Moemen.
Thank you.
Really helpful. All right, so let's shift to our second optimization here. I'm really excited about this one because I received a lot of questions kind of that will be clarified with this optimization. All right, so selecting the right battery technology for use cases, right? Oh, and let's not forget about our famous quote here. So lead acid batteries are perfect for UPSs, but a terrible choice for ISO ancillary services. Nikola Tesla himself has said that. Just kidding. It was still somebody we don't know, but somebody did say that. All right, let's get into the meat and potatoes here. So in this optimization, we're assuming now a kind of a 2-cycle application. So we wanted to, the last optimization we had 1 cycle a day, right? We did 2 cases, deep discharges, shallow discharges. Now we're doing like a different type of use cases, 2 cycles a day. You're doing deep discharges, and then you have 1 or 0.1 cycle doing kind of very rapid charging and discharging, which is indicative of frequency regulation. So with a use case like that, what becomes your optimal battery choice? So what we've done here is simulated the case through Storlytics software. And here you're going to find that we added here the Sankey diagram or the loss diagram. And the reason that's important for both the lithium case and the nickel hydrogen technology case is there is a significant difference in amount of losses between these 2 technologies. That's why we really need to look into where the energy is going. So just for everyone's background, here, this is the charging portion. So charging from the grid and then going through the inverter, then through the battery terminals, and then kind of through basically a ideal battery, and then discharge back into the grid. And as you go through these different steps, there are losses here. So a couple of points to mention here. We assumed, again, to keep the comparison focused on the technology selection, we took out auxiliary load. And we're focusing, and also for the inverter, again, because we're using, in both cases, the same exact inverter. We just assumed it's going to be an ideal inverter, so almost no losses. So that really keeps the focus on the battery technology itself. So as you can see here with lithium, you're getting much higher than that 92% we're used to with lithium without the HVAC load. And that's mainly because it's a high cycling application. You're not kind of spending any time just sitting there. But kind of in addition, we can see that with the design we set here, we're meeting 100% of the usage profile we inputted, right, which is this one. So we know our system is adequate for the use case. And now let's start looking at the degradation here. So here what we found is, all right, for a 20-year project life, we reach 65% at year 20. And to get to that 65% and to have a viable project for 20 years, we needed to have 61 megawatt hours. So I think we're good from that standpoint. We're meeting really all the requirements of the use case. And just to clarify, since we're accounting, we wanted to account for the depth of discharge here of lithium. So we're really shooting for 444 megawatt hours as a minimum, or 65% state of health. So whichever comes first really causes you to add more battery racks to your project. So in this case, really the 65% came first. So that's why we have this much batteries. All right, now that's for lithium. Let's switch over to nickel hydrogen, right? And in this case, the OEM is Enervenue. Folks may be aware of them. They're getting a lot of press, and they're really doing a great job with their product. But all right, let's see how it performs. Now, again, we're focusing here on the efficiency of the system and losses. And what you see here is that within the battery, you're getting more defined and more significant losses, both when charging the battery and when discharging. So orders of magnitude, well, not orders of magnitude, but significantly more than lithium. Now, what you see here as well is the energy capacity in this adequacy radar went down a bit, and that's because the system that we defined here is much less efficient than lithium. Again, we were assuming a 92% round trip efficiency when we developed the POI profile. But since this is kind of less efficient than that, you start to get data points where you don't fully meet the POI profile. But anything above really 90%, we're really good with. So we consider that we kind of met the profile here. All right, so now the degradation, right? So in order to get to and maintain 400 megawatt hours, we only needed 450 megawatt hours worth of nickel hydrogen batteries, right? So I think the last case we were at, I think it was 500, or no, it was actually 800 and something for lithium. So you can see quite the difference there. The other difference you'll notice is that throughout the years, here you only degraded down to 93%. For lithium, this was 65%, right? So in addition to kind of the maintaining the required energy capacity at the POI for 20 years, you're also degrading much less throughout the years. So you spend more years having more energy capacity that you can utilize. All right, the summary here. Adam, I'll pass it over to you.
Yeah, a lot of info on here, but Sherif and Moemen, great job kind of pulling together the details there. Really interesting to kind of compare lithium to intervenue in this case. The first thing I want to point out, though, is, as you guys have shown, is that this optimization 2 between intervenue and LFP really did consider it running at 2.1 cycles. So I did show here the 1 cycle deep discharge. So what you're seeing on the far right in the yellow is, so the comparison being kind of for LFP, you would need to add another 140 megawatt hours to account for the now 2.1 cycles that you need to run per day as opposed to 1 cycle. So just want to kind of clarify that if there's confusion on this slide. So now kind of looking at the financial results, one thing, and we didn't have the financial assumptions here, but earlier we were assuming $200 per megawatt hour for the battery portion of the CapEx previously. And we're still doing that for LFP here, but we are assuming $350 per kilowatt hour for the intervenue product. You know, I'll stand behind these numbers again. They're for illustrative purposes, but the idea is that this non-lithium technology is more expensive. We also are assuming the same operating cost from a kilowatt hour perspective. Again, that's something that would need to be kind of verified. But what we wanted to really show here is that the difference in degradation and round trip efficiency can really impact the returns here. And that's what's really shown here. And so, and I say degradation because it impacts the initial upfront overbuild. And so you need significantly less initial upfront overbuild with the intervenue product than you do with LFP. That was clear from Sherif's kind of comments, you know, just now. And the impact of that on investment returns is, you know, this is clearly kind of the front runner in any of these 3 cases with the 5.8% IRR compared to 2.5 and 5.1, right? And really it should be compared to the 5.1 because in this case, the utility doesn't really need more than 1 cycle, but that's probably not going to have much of an impact on intervenue because it degrades so little even doing 2 cycles per day, right? So that's the point, but there's something we're not accounting for here in these slides, and that's the round trip efficiency. And so in the case where you have a toll agreement with an offtake utility, you aren't really paying for that on an ongoing basis, more than likely. It's something you negotiated up front and why you were able to offer that $15 per kilowatt month offtake agreement rate, or PP, if you want to call it a PPA rate, you can, in the first place. And so you probably would have needed to come under that given the less round trip efficiency that the interview product has. And so what we did here is we calculated sort of a round trip efficiency penalty, and that was calculated assuming 5 cents per kilowatt, or 5 cents per kilowatt hour multiplied by that efficiency difference. And then, you know, per day, per year, et cetera. And so again, assuming sort of a 5 cent kind of retail rate that this project would kind of pay as a penalty. And so now that dynamic changes. And now because of the, I would say, better round trip efficiency of the lithium product, you can see the investment returns would point you to really the initial deep discharge example shown. So, you know, again, the point of this is these details matter. Round trip efficiency in this case, just comparing 2 different technologies, and they need to be considered when you're pulling together economics and making these decisions up front.
Yep. Absolutely. So, Adam, thanks for clarifying kind of that balance between round trip efficiency and what you're losing in terms of, you know, cost of energy over, you know, the entire project lifetime for both cases, and really putting a dollar sign on that versus, you know, how much less maybe you have to pay for the battery capacity because it degrades much less. I think that dynamic kind of heavily depends on the use case itself, and it's great to kind of be able to see when you reach an inflection point between the 2 and really what ends up being the best case for you. All right, so that basically concludes the optimization too. So I think we can take a couple of questions here. So there's a question in the chat here. Is charge and discharge cumulative percentage the battery state of charge? And that was from Lynn Apollos Laurent. And I think actually this may be referring to really way back. And I'm sorry if we missed this earlier. Yeah, I think this is referring to this cumulative percentage. So I'll just add some clarity here. So there's two of these cumulative distribution functions. This first one is for power set points. So what it's basically doing is it's looking at all discharge power set points and basically putting them into buckets. So in blue here is the histogram, and in orange, this is the cumulative distribution function. So what this is saying is basically, if you're at 700 or I'm sorry, 7 megawatts, you basically have a little more than 80% of the battery set points, power set points rather. And you only get to 100% if you're at around 8 megawatts, right? So there's no really state of charge here whatsoever. I think, on the energy side, right? And I'll just clarify, this is coming out of the battery profile creator. So this is basically just looking at, for each day in that profile, right? What was the discharge throughput? What was the maximum charge throughput? And if you put those into a distribution, right? The discharge energy per day, the charge energy per day, how that ends up looking. So here in this case, our sample, I think Moemen, this was probably what, 365 days or so, or maybe it was 30 days. But the more number of days you have, the healthier the sample, obviously, and kind of the more defined this distribution is. So to answer your question, state of charge, there is no state of charge here. This is just looking at the usage profile you have. So you'll get a better view at state of charge once you kind of model the system in the system modeler here. Right, I hope that helped. And I think we can take one more before moving on here. If we extend the lifetime beyond 20 years, would the model provide a degradation in state of health curve? Yes. So I think here you can set this to 30 years, but as you view the results, so for instance here, right, we're getting into 54% state of health, right? And we know that our end of life for our batteries is 65% state of health. We just defined that for this workshop across the board, but like I said, it differs from one battery OEM to the other. So this was kind of the first run here. So you'll notice that we went back and added more battery capacity, not changing the battery profile. So when you actually add more battery capacity, that means you're using less of the state of charge range, which means you get less degradation, right? Which means you're able to extend what kind of the state of health to further years in the future. So long story short, to answer your question, yes, it'll go beyond if you simulate more years, but as a user, you want to be able to recognize when the battery state of health is going beyond the performance guarantee of the OEM. Now, one thing you'll learn, and this is really getting into the weeds there, with most LFP OEMs, they will tell you, yep, you can use our batteries beyond 65% state of health, but we just won't guarantee it. So you're really taking a risk there, and you're opening yourselves up to like operational challenges, balancing challenges between racks and inverters. So you should, if you plan to do that, you probably want to account for more downtime, more O&M costs, because it's going to be difficult to manage a system outside of its performance guarantee. All right, I hope that helps. Okay, I think we can probably move forward to optimization 3 here. Sorry, folks, we got a lot of slides.
Yeah. Hey, Sherif, what happens when a battery commits a crime?
I don't know what.
They get charged.
Oh man. Oh,
That's all I got.
Wow. Oh boy. That's gonna live in YouTube forever. All right. Optimization 3. So the famous question, augmentation over versus overbuild, right? To augment or not to augment? That is the question. Shakespeare, but not the one we all know about. Okay, so in this case, really what we did is we did a 1 cycle a day use case. This is similar to kind of the first optimization. And in this case, we're using CATL as the benchmark, or the battery module. And very similar parameters to all previous simulations: 100 megawatts, 400 megawatt hours required to be discharged at the point of interconnect for 20 years. So when this was simulated, you may remember these numbers from the first case we ran. We found that we needed 712 megawatt hours at beginning of life for our project to last for 20 years. Right? So now if we're trying to do the exact same, only with an augmentation strategy, right? What is that going to look like? And in this case, we're assuming a DC augmentation. There's a bunch of different augmentation architectures out there. We have a section on that at the end. Don't miss it. I think there's a lot of good information in there and a lot of lessons learned. But for here, we're just going to assume DC augmentation, since we see a lot of folks kind of assuming that, not really realizing what's entailed there. But here we're just looking at it from an energy standpoint, right? If you put all the risks aside and you're planning a DC augmentation strategy, what do things look like? So just some ground rules here that we're going to set. You know what? I think I didn't grab the right slide. But anyway, so here our rule is that we're going to allow our batteries to degrade down to 65% for all phases. We need to have at least 444 megawatt hours at the battery terminals. So this is accounting kind of for losses between the point of interconnect and the battery terminals, and we're also accounting for the depth of discharge there. So basically 444 is basically 400 divided by 0.9. That's where kind of this number is coming from. So basically that second rule is the total capacity has to always be greater than 444 megawatt hours in this column, right? So what we did is we ran the simulation, looked at phase one, and basically sized the system so that it degraded down to 363. And I'm going to cause some confusion here, but in the slides you receive, you're going to see something slightly different. We actually allowed it to go down to 65%. So you're going to see this column kind of a little bit longer, and this is 130 megawatt hours instead of 110. But really, the three phases here, with the three phases of augmentation, you have adequate capacity throughout your battery project. Here in year 13, we're assuming a replenishment is going to happen, and that means basically we're taking the batteries out and just putting new ones in. That's why you see kind of a significant battery capacity being added here in phase 3. So that's kind of the overview of the execution strategy. So Adam, I'll pass it over to you to kind of go over the financial side of things.
Yeah, and just to point out, and Sherif, we had a little bit different slide there at the end, but maybe missed getting that one in there. But we're really augmenting at year 5 and 15 for this exercise. You know, again, you can iterate so many different ways here on upfront sizing and when you iterate, and it's important to do so. But what we wanted to show you are the assumptions made here when we show you the financial results here in a couple of slides. And so that is that in year 5, when we augment, we're doing it at a cost of $200 per kilowatt hour. That is intended to cover the battery supply and the EPC costs that you would realize. There wouldn't be any PCS costs because, as Sherif mentioned, we're just doing DC only. So we've designed this project up front so that we didn't need to add any additional inverters. So that's the cost assumed in year 5, and then the cost assumed in year 15 is $160 per kilowatt hour. These are also assumed to just hit the operating expense line item on the financial pro forma. So they are treated as operational costs. They're not treated as capital costs, so there wouldn't be any depreciation benefits. There wouldn't be any. There is no ITC applied here. You know, arguably could probably qualify for those types of things, but I'm just telling you the assumptions made for this case. So what we did here, though, is if you look at these lines, right, the orange one is the overbuild and the blue is augmentation, and you're like, okay, well, so overbuild was higher, and that's because you installed more cells with the initial overbuild, so your ongoing operational costs were lower, as we discussed earlier in the webinar. But that's not really true here ongoing. So, you know, we made this mistake, you know, realized this mistake as we were going through these exercises. And now, Sherif, if you go to the next slide, you'll see the blue line kind of pops up. And so we accounted for the fact that, hey, we installed more cells in year 5. We need to bump up those LTSA costs because we're servicing more batteries. Same in year 15. And what you'll see is this impacts the IRR by about 60 basis points. So now if we can go to the kind of the final slide here, Sherif, where we're comparing the results. Again, initial oversize for the overbuild 712 megawatts versus the augmentation is 516, but then adding, as Sherif mentioned, 130 megawatt hours, and then replacing really the entire system in year 15 at 400 some. The CapEx total, and this is just the initial, is 220 versus 164. The OpEx that we're showing as kind of an annual 20-year average, which includes that augmentation, is, you know, significantly higher, not surprisingly, and is approximately 4.7 million in addition for that augmentation. So now, okay, think about, okay, so what's my return doing the initial overbuild versus doing augmentation? And the answer is at least directionally, we would say here is 5.1% compared to 4.9%. And that includes if we wouldn't have caught that mistake of adding in the additional cells and adding in the additional LTSA fees, we would have thought it was 5.5%, and maybe would have selected the augmentation strategy instead of the overbuild strategy, right? That return looks better at 5.5%. But what we missed here, and really comparing apples to apples, is if you are going to kind of roll the dice versus taking the kind of less risk approach, the less risk approach of overbuild typically comes with an opportunity to purchase a capacity maintenance contract, a capacity maintenance agreement, or kind of, which comes with a fee, which sort of guarantees that you're going to have 400 megawatt hours at the POI. We did not include any cost for that. And so, if you can click one more button there, Sherif, we didn't add any fees to the OpEx here for that overbuild that would maybe kind of guarantee you that 400 megawatt hours. And so, that would impact these returns as well, and isn't included here, but it's just sort of another sort of caveat and sort of fine detail that needs to be thought of and included when you're making these decisions of whether to overbuild or augment, and how you're looking at different strategies. One of the, and I'd be remiss if I didn't at least wave the Flexgen flag a little bit here. One of the benefits with Flexgen is, I mentioned that we're hardware agnostic. So when you make that decision up front, hey, today we're going to go with this hardware, but you may not know who you want to use 5 years from now or 15 years from now, because we're really centric on the energy management system and the software, and we're flexible to who that new hardware might be in the future. What's important from our perspective is to make sure you select the right operating system up front, so that you have that flexibility for augmentation in the future. I know, at least, just kind of going back to my Duke Energy days, it was a matter of like only 3 years of developing energy storage projects there, where I won't name the vendors, but we only worked with vendor A at first, and they were in NMC chemistry. And by the end, before I had departed, we were only working with, I would say, vendor B and LFP chemistry. And so that dynamic is going to continue, and you don't really know who you're going to be using 5 years from now, certainly not 15 years from now. And Flexgen really offers that flexibility with the hardware to have that augmentation strategy be intact. Sherif, pick this apart here, man. What am I missing here?
No, I don't think you're missing anything. I like the point you made on, really, if I'll summarize it, if you're going to plan for one thing with grid-tied batteries, plan for change. Know that what we're doing today is going to be very, very different from what we're doing next year or the year after. So, yep, I definitely kind of value and I see where the value is with systems that are agnostic, that allow you to kind of make changes throughout the project life, because it's a very rapidly evolving supply chain and industry, and also it's a very rapidly evolving grid, right? Look at the amount of EVs that are being added, right? As Duke Energy, a regulated utility, we have that kind of right there, and we're planning for it. But again, things are changing. So I'll just say this another time: if you're going to plan for one thing, plan for change.
Yeah, no, great point. And to maybe answer a couple of the questions that I'm seeing in the chat, I would say also it is more helpful if you use the Q&A versus the chat, but I do see a couple of these in the chat. What about the risk that there are not compatible batteries for installing at year 15 in the existing racks? And my answer to that, I'd be curious to see what you say, Sherif, but if you design it up front such that your inverters can accommodate additional DC capacity, you wouldn't necessarily need to use those same racks. You would just you can add an entire additional container that then connects to those inverters. And typically, at least at Flexgen, we like to design our systems initially to allow for that.
And we're going to get into the weeds of that in the next section here around different augmentation strategies and what are the pros and cons of each. I'm really, it's a topic that's very, very dear to my heart because at Duke Energy, we did a very comprehensive review of really the options that are available to us in the market. And we did a financial review and a technical review. I'm just going to focus on the technical side since we already went through the financial side here, but I would suggest to people just to stick around for that section because there's a lot to account for there and a lot you want to be aware of before just saying we're going to augment.
Yeah. And what if I can answer one more maybe before we dive into some of your augmentation strategies, Sherif, is the question on, are you considering DC or AC augmentation strategy? We've really only talked about DC here. And part of the reason for that is if you go AC, that means you're adding more inverters. If you're adding more inverters, you're changing the dynamics of what you agreed to in your interconnection agreement. And you then likely need to file an amendment. And hopefully, and then at that point, you may trigger a material modification, and then you have to go through an entirely long, interconnection sort of process to get that change approved. Is the likely result of if you don't plan, that's sort of the impact. If you don't plan up front for DC augmentation, then you will be forced to do AC augmentation and deal with the headaches of going through interconnection processes.
Good point. All right, I think before we move to kind of the next section here, I guess, Adam, I'll pose one additional question to you because I think it's just so important. I think a lot of the results we see here depend on these 2 points, right? The forecast for battery pricing in the future and our crystal ball. Right. So can you speak a little bit about that and what's the level of confidence we have?
Yeah, great question. Just kind of high level, right? I think your tier 1 suppliers, well, I don't want to talk like that. I guess I would say, I'm not going to give expertise on like what I think the pricing is, and do I personally, this is Adam Nygaard speaking, not from personally, but I think 200 kilowatt hours, including battery costs and EPC 5 years from now is going to be achievable. That's just my personal opinion, but you have to make these assumptions yourselves as developers and product designers and the pro forma financial modelers. And it's important to kind of be able to have why do you believe that? Do you believe in a Bloomberg New Energy Finance cost curve? Do you believe in a Wood Mackenzie cost curve? Those are that's the kind of evidence that I suppose you would have in the background as you go to your investment committee and say, hey, this is what we believe, and this is what we're kind of underwriting this investment to meet is kind of based on this information.
Yep. Agreed. All right, well, let's, I'll just take one question here. So Walter Chang asked, when we charge and discharge from the grid and distribution system, do we need to pay transmission charges? If I understand that correctly, in tolling agreements, and Adam back me up on this, but in tolling agreements, it's typically, it may be limited to a certain technology. In most cases, it's going to be limited to lithium. So the round trip efficiency somewhat, well, it's known, the utility knows what to expect. So they won't really charge you for the energy you're charging your battery with, but you will be charged at kind of regular rate for the auxiliary load, your HVAC load. So you'll have a separate service for your auxiliary load to kind of pay for that.
Yeah, I would say I think the answer to this question is it totally depends on exactly where your project is located, what utility it's connected to, whether you're participating in a merchant market and maybe you're kind of getting paid for providing one of these services as opposed to like
you need to just charge on your own, and to be able to only serve a discharge function that you're getting paid for later. Versus what Sherif mentioned, we've done a lot of example here around toll agreements where maybe the off taker is responsible for those charges. So I hate to, I always hate that answer. It depends, but that's certainly a it depends answer to Walter's question there.
Yeah, a lot of people say there's never been a conversation around batteries without it depends being said at least one time. So I'm glad we were able to say that today. It means we're on the right track. All right. Let's go ahead and move on to the next section. All right, there's more to augmentation than just adding batteries. It's truly the case. All right, so here, all right, there we go. These are just some general risks that you have to consider when thinking about augmentation. So difference in voltage profiles between new batteries and old batteries. So it's just one thing I'd like kind of all the attendees to be aware of is, battery cells voltage will change throughout the state of charge range. So there's going to be a maximum voltage at maximum state of charge and a minimum voltage at minimum state of charge. So that voltage profile will change with time as the batteries degrade. So when you parallel a new battery with an old battery, right, you're paralleling basically two different voltages. So what happens? You start getting, charging from one to the other, you need to balance, and it's a nightmare for the battery BMS. The integrator won't like it very much. They'll lose a lot of hair over it. So it's really a big risk. And I love it when, a lot of the, planners and will assume that, oh yeah, we'll just move all the old racks together and parallel them as if nothing happened throughout the project life and all racks discharged exactly the same way, charged exactly the same way. None of your inverters went offline. It's a really, really optimistic view, but we'll get into that later when we get into the details of that architecture. All right, another thing, form factor variance. This is kind of more applicable if you're planning to just kind of buy battery racks and put them in the same building or the same enclosure. You may not need to worry about that so much if you're using kind of a single rack enclosure like the NR1 the CATL battery solution is just one enclosure per rack, so you can just that's not as big of a deal. But certainly if it's a ISO container or a battery building, your form factor is going to be a factor there. Another one that gets very, very often missed is difference in fire protection and safety requirements between old and new battery systems, right? We all know there's kind of a lot evolving in the fire safety space. There's been a lot that has changed in NFPA 855 over the past, I want to say, 3 or 4 years. So when you're planning an augmentation strategy, you're probably at least planning like 5 years out into the future. So it's very, very likely that we'll have different safety standards then that may affect how you're connecting your new batteries. Right, performance guarantee terms variation. So those by single source vendors, which is the case for. Yeah, so as most folks are aware, when you go out and purchase a battery system, you're purchasing it with a performance guarantee. So you have that coverage you're aware of. That is probably not going to cover future states. I find it, in my experience, we haven't found any integrator that's willing to kind of guarantee the performance of batteries that they are going to add 5 years from now, 10 years from now. So really, if you're planning an augmentation strategy, in most of the times, you're planning for that on your own. You're going to go out in 5 years, you're going to get a contract with another battery integrator, or procure the batteries yourself and have a EPC kind of install them for you. You're taking that risk on your own. There isn't many parties out there that'll, at least bankable, right, that will tell you, oh, yep, year 15, we're going to be there and we're going to be adding these batteries. You're not going to find that. So be prepared to take that risk on your own. Right, and the consideration as well, last one here, is that with augmentation, you have differing capacities throughout the project life. So just plan for that, kind of like Adam alluded to, right? With AC augmentation, you're adding actual more inverters. So, you're ending the project capacity at a different power capacity than you started with. So it's not as big a deal, I think, from a technical standpoint, not an interconnection standpoint. But it's also something to be aware of. All right, so the first approach here we're going to talk about is DC augmentation, right? And I'll just call this 1A because there's a couple of types of DC augmentation. But here, what you're assuming here is that, all right, these are all the PCSs throughout the project, right? We're assuming that, all right, we have 10 inverters. At the first augmentation, the plan is we're going to take the battery racks behind that 10th inverter and just scatter them across all existing battery racks behind other inverters, right? And then the new battery racks, we're adding them behind inverter number 10. So that way, remember this first point, difference in voltage profile between new and old battery racks? That way we didn't parallel the new battery racks with the old battery racks, right? So here, these yellow and gray racks, they're parallel together, but that's okay, right? Since, they all, they were put in service at the same time, so they must have degraded the same exact way, right? Well, no, wrong. That's a very, very dangerous and optimistic view, right? If you've operated any battery project, you're going to know that not all inverters are going to be on 100% of the time. You're going to have one inverter that goes offline for a couple of weeks, maybe a couple of months, till you get that IGBT from the OEM and it gets fixed. Meanwhile, all the other inverters are operating. So at the end of the day, it is more realistic to assume that these will have varying levels of degradation and accordingly varying voltage profiles across them. So when you kind of take all these racks that have been treated kind of the same way since they're behind the single inverter, and you disperse them in parallel with the others, there is like a very probable and likely case that the voltage profile of this yellow one is different from these gray ones here. So long story short, just to summarize here, the pros and cons, strategy reduces risk of rack voltage imbalance since old and new racks are not mixed. Augmentation involves minimal equipment type. So here, if you look at it, you're only adding battery racks, right? So that's a good thing. You're not adding any additional equipment other than just batteries. So that is an advantage. However, like we said, it's very optimistic to assume that you'll have the exact same voltage profiles across all the racks. Second on the cons list, since some inverters will have, well, this is actually the one we discussed. The other thing is the one we kind of touched on here as well, the form factor, right? If you're in a building, if you're using an ISO container, you're assuming that the battery racks you're adding are have the same form factor as the old ones here, and that's very, very unlikely. So that concludes kind of the first augmentation approach.
Yeah, and Sherif, I just kind of want to mention, right? I gotta put in my shameless Flexgen plug here. You talk about the risk of like voltage imbalance, and you might have older cells that are degraded more than others, right? But the way to kind of mitigate some of that risk too is really through having a solid energy management system, and one that is monitoring these. At Flexgen, we're collecting 15,000 data points per second on our systems, and it's taking that data, seeing what's really happening at the cell level, and then responding and sending the right commands to these cells and modules to deal with these imbalances and differences really at the cell level. So again, just kind of want to enforce that energy management system is what's dependent on balancing all of this and keeping it kosher.
Oh. Right. Yeah. Thanks, Adam, for that. Now, I'll add, in the beginning, I mentioned this is, a DC augmentation A. DC augmentation B is where, you have DC-DC converters to help you with that voltage imbalance. So the way OEMs and integrators are going about this is one of two ways. Either in the beginning of the project, they assume that there's going to be, they're going to have DC-DC converters behind each inverter and on each rack. So on top of each rack, you have a DC-DC converter. So really, that rack could have whatever voltage profile it wanted because you have that DC-DC converter kind of taking care of the voltage imbalance between all racks that are connected to a common inverter. So that's one way. The other that is slightly similar is you'll only add DC-DC converters to the racks in which you're mixing old ones and new ones, or you're mixing old ones and other older ones. So here you'd be adding DC-DC converters as well. So that will kind of help you out with the voltage imbalance issue. Although something to consider with this architecture and just let's remember why we're doing this. The main purpose of augmentation is that you're trying to defer, that investment into the future. So you're trying to defer capital. So with that DC-DC converter, you're kind of going in the other direction. It's as if you're adding an entirely additional layer of DC-DC converters on top of, or entire additional layer of inverters, really, because they are on a dollars per kW standpoint, they are kind of at a similar price point. So again, it goes against the whole reason we're doing augmentation. So personally, not a big fan of this solution, but I mean, there could be cases out there, and there probably is cases that makes sense. Just depends on the use case. All right, now AC augmentation, right? So let's talk about like the architecture itself. So what are you doing here? You're just basically building out a project at year zero, right? If you're planning for it from year zero, you're just building the project and leaving space for additional inverters and PCSs to be added and battery enclosures behind them. So physically what you would do is you would build the medium voltage collection system such that it has capacity for all the future phases you plan to add. So that's physically. You'd also account for that additional power capacity, again, for all phases in the GSU capacity, so that when you add more PCSs, you don't have to upgrade your GSU if it's transmission tied. So that's physically. Now, I guess I'll call it just logistically. If you're planning an AC augmentation from year 0, you probably want to structure your interconnection accordingly and request the full capacity of all phases. Now, different utilities may have different requirements and limitations on this from an interconnection standpoint. Some utilities may tell you, well, no, you can't actually reserve all that capacity and, for 5 years and then, add that capacity, in the future. You have to have like the amount of capacity year 0 has to match what you have your interconnection for. Other utilities may tell you it's fine, only you just have, these requirements from a SCADA standpoint, from a system design standpoint, so that their system impact study results aren't invalidated when you add more inverters in the future. So it'll just differ from an interconnection standpoint. So if you're planning an architecture like this, check with your utility, but it is definitely a bad idea to plan for this strategy and just have the interconnection at the capacity of only the first phase. And then after 5 years, you're submitting another interconnection and going through that process again. A lot of risk there. So I think that covers this one, both from a pros and cons standpoint. Mohamed or Adam, anything to add on this one? All right. Okay, so I think with that, we can probably take a couple of questions.
Sure. Do you want me to start off with a couple that we have here?
Yes, please do, Christina. Thank you.
All right. So Alejandro Gutierrez asked, when we evaluate augmentation, we identify the risk that in the future there are no compatible batteries for installing in the existing racks. Do you know what has the industry, if the industry, has done something to prevent this issue, or how they are tackling it?
Yeah, so different kind of entities. I'll just give my perspective here. Kind of for us as Duke Energy, we recognize that as a big risk. So with specifically with DC augmentation. So really for our projects, we're planning AC augmentations, at least right now, and we're continuously evaluating new architectures out there. It also depends, one thing to take into account and to consider is how big are your inverters, right? The smaller your inverters are, the more flexibility you'll have with kind of the riskier augmentation strategies, which in my view is DC augmentation. But really, it becomes using smaller inverters isn't very economical, especially when you're designing kind of hundreds of megawatts of projects, or your project is, I would say, like 50 megawatts and beyond. So yeah, it depends on your specific case.
Perfect. Well, thank you. Adam, Moemen, would you like to also add something else, or should we move to the next question? Okay.
No, I think just to reiterate that energy management system is pretty important in being able to efficiently augment later on too. But yeah.
Perfect. Well, thank you both. So the next question comes from Huda, and she asked, how do you incorporate forecasting and modeling techniques to ensure accurate project design and performance evaluation?
Forecasting. I'm not sure if she means price forecasting or load forecasting, but I think from a modeling standpoint, at least at Duke Energy, we're trying to be as accurate as possible with modeling these battery systems and forecasting and estimating their degradation based on exactly what we plan to do with them. One of our challenges as a utility is that we operate the grid. So when we install a battery project at a certain location and we're planning in the beginning for that battery project to, like, for example, provide backup power to a town, like, for example, our Hot Springs project in North Carolina, right? If something changes on that feeder, which happens, right? You get more load coming in, us as a utility, we have the responsibility to basically accommodate it, and it'll probably lead to a change in the use case that we're implementing for that battery facility. So maybe instead of it doing peak load shaving for the other 99% of the time when it's not providing backup power, maybe now it needs to do a frequency regulation function or arbitrage function. So that was really one of the challenges we had when we were starting this energy storage program. Everyone in the industry or really developers really knew exactly what they wanted to do with their batteries because they're planning for a certain service. But us as a regulated utility, we wanted to have flexibility. So we spent months and months negotiating flexible, what is now very well known as flexible performance guarantees with battery OEMs. But that's for the execution phase, right? When you have a purchase order in hand and you're talking to a major battery OEM like Samsung or like CATL, and you're telling them we want that flexibility, they will work with you. But if you're in the design phase, which we're also doing, right, and you want to estimate, all right, for this use case, how much degradation we get versus that's where you kind of need a little bit more sophistication here. And that's kind of one of the major points here of the workshop, specifically the first optimization, where we looked at two different types of cycles and how it impacted degradation.
Yeah, and just to kind of touch on this a little bit, right? So the question is around forecasting and modeling. I mean, the modeling is what is happening here with this Storlytics tool, right? The forecasting is different, right? Sherif just gave you a perspective of how a regulated utility looks at forecasting and really how they're thinking about developing that battery usage profile. The major point of this whole webinar is that the battery usage profile can make a huge difference on your sizing and project economics, right? But so again, Sherif gave the regulated utility perspective, but there's a ton of people I'm sure on this call that are either under a toll type of agreement, they're an IPP that has a toll agreement, or maybe you're operating merchant. And so from a forecasting standpoint there, that's especially in a merchant market, I'd recommend maybe like an Ascend Analytics or maybe a Customized Energy Solutions, who are really the experts on sort of pricing different nodes to help you develop what you think your battery usage profile is going to be to maximize revenue in wherever you're placing that battery, whether it's CAISO in the United States or ERCOT in the United States or elsewhere. We'll just kind of throw those names out there. Those kind of firms can help you develop that battery use profile that then feeds into this Storlytics tool that then also needs to be fed into more of an economic pro forma. Hopefully that's helpful in kind of shedding some light on that question.
Great. Well, next question is also from Hoda, and they ask, how do you determine the optimal sizing of the energy storage system and select the appropriate battery technology and original equipment manufacturer for a specific use case stack? I'm assuming that there's a lot of different factors that are depending on, and there's no general view, but do you have any tricks out there that they could use?
Yeah, I think kind of, well, that was kind of the main subject of this workshop. And we'll be happy to kind of share these slides afterwards. And if you review the recording, you'll see kind of optimization 1, 2, and 3 will basically specifically addresses that question. But the only thing I'll add is, prior to getting into a study like that was conducted for optimization 2, where we compared Enervenue to lithium, right? Prior to doing that, as you kind of design more battery projects, you become aware of how use cases are affected by different characteristics in the battery that you use for these use cases. So if I know that, for example, right, technology like Enervenue, right, the nickel hydrogen technology, it has a high self-discharge rate compared to lithium. So now I know that, all right, I probably don't want to use that technology for a backup power application, because in backup power applications, what are you doing? You're just basically charging the battery and waiting for an outage, right? So you don't want to have a battery technology that has high self-discharge rate in a use case like that, right? But we know it has a very, very high cycle life. So if we have a high cycling application, now we know, yeah, it's probably going to be either, this Enervenue technology or maybe another one that has a similar high cycle count characteristics. So that's your starting point, but then you want to get into the details as we did in this workshop.
Okay. I also see in the chat, Carmina asked, what is a long-term LFP cost scenario used for modeling augmentation?
What is a long-term? I can't see that question.
Oh yeah, I see it in the chat. Yeah. So we talked about that. I'll ask Sherif if you can go back to the graphs. So it was kind of bundled together, but no, keep going back. I think 1 or 2 more. Yeah. See, so on the right hand side. Yeah. No.
Yep.
Keep going 1 more, Sherif.
Oh, here.
Yeah. So we assume $200 per kilowatt hour in year 5 and $160 in year 15, but that is also supposed to represent the EPC costs that you would see to, add in those batteries. So that would be LFP BESS plus EPC costs there. We didn't necessarily go through trying to separate them out, but.
Okay. Yes, Carmina confirmed that it was answered. Yep. Thank you.
All right. I think we can take more questions here. Luckily, we have some time. I think this one, it's actually directed towards me, but Adam, since you kind of have that Duke Energy business development manager, history, I think you'd be better to answer this one. So
Duke. So yeah, I can answer this. So when I said I worked for Duke, I was on the regulated utility side, and so what that means is Duke doesn't compete in a market. There is no price point to determine when you should charge or discharge. It's really like the Duke system operator decides when energy is needed or not, right? And so Duke on that regulated side means they're a regulated monopoly. Like you can't buy your power from anybody else in North Carolina, depending on exactly where you live, I should say, other than Duke, right? And the reason they get to do that is because they're regulated by, for example, the North Carolina Utility Commission. There's other southeastern states in the US are regulated like that as well. So they're allowed to make a certain return on the investments that they make to the grid and to batteries, other power generation applications. And so what Duke does on the regulated side is they have to go to that state regulatory commission and say, hey, we want to do this project. These are the benefits to the customer, and then get approval from that state regulatory commission. And so the projects that are on Duke's regulated side of the business have all been, I would say, approved by that state regulatory commission that either said, hey, this is in the best interest of the rate paying customers. Alternatively, there are storage projects on Duke's commercial side of the business, which again was just announced 2 days ago, or no, I'm sorry, it was yesterday, that it was being sold to Brookfield. That side of the business is operating in competitive markets where, you know, they need to meet I would say, a target IRR. The financial metrics of success are different on that commercial side versus on the regulatory side, on the regulated utility side. So just kind of want to point out that difference. Hopefully that answers the question.
Yep. Thanks, Adam. I'm very glad you're here to answer that question. I'm more on the technical side within Duke. So
yeah, that's fair. Well, I was the one in front of those. I was the one in, you know, at those state regulatory meetings trying to convince them we needed to invest in batteries. And fortunately, we were successful, Sherif. But it was only because you guys on the technical side designed such great battery projects.
Awesome. Thanks. All right. Let's take this next one here. Can you explain?
I can take this one. So can you explain the process of assessing impacts of energy storage project on project IRR? What you really have to do is, I'm glad you asked this question because, you know, Sherif and I had a conversation about this, and Sherif, you have to try to help me remember what was the metric that you were previously going for?
Yeah,
it was
we're looking at the net present value of all OpEx costs plus capital costs divided basically by end of life usable energy.
Yeah. And so yeah, so well, and Sherif went through that sort of early on in the deck, right? But what isn't accounted for in that type of analysis, well, I get he did have the net present value. So net present value does take into account the time value of money. But the point is, or really the answer to the question is, you have to have a model that basically shows cash flows, both revenues and expenses over time, that can be dynamic such that when you make a change to size, it changes both CapEx and OpEx costs of those cash flows over time. And the difference when you make changes to system designs and change those cash flows, that's how you will understand the impacts of those changes to the IRR. Because essentially all IRR is a calculation of it calculates just the cash. It's just at the end of the day, the cash flow to the investor across some period of time. Is in regards to associated risks and possible mitigations, you know, that's very contractual. So, you know, maybe that's a good question to go to one of our last slides here, Sherif. Which I think is kind of a summary getting back to, I don't know if you added any more in there. No, keep going. It's kind of like, you know, we started with this is a terrible investment committee slide that you would get laughed out of the room at, and not saying that this is a whole lot better, but now our mitigants are a lot more detailed, right? Before, our mitigants were, oh, well, we're just going to make sure we design it good, right? That's not an appropriate response. Now the appropriate responses are, well, our PCF sizing is sized to meet 20-year requirements without augmentation, or it's sized that we added that extra PCS inverter, as Sherif just walked through, to allow for augmentation in the future, right? And that's going to mitigate the risk of triggering a material modification later on down the road. So, you know, that's a risk that you know, you can either mitigate it up front, or you can assume that risk and know that you're taking that risk depending on what happens in the future. Similarly, you know, for the battery sizing, And we walked through a lot of these, the risk of the sizing being inadequate, and then you fail the offtake capacity test. The additional consequences of that are either you're going to need to pay financially liquidated damages to that offtake agreement owner, or you're going to need to remedy the situation and go buy new cells and somehow meet that minimum requirement, right? There will be financial pain there. So to mitigate that, we now know how to overbuild and design for, we can tell the investment committee, well, this is the worst case usage scenario, the deep discharges every single day, versus maybe a better case. And either you designed a project that was maybe somewhat in the middle, and you're telling the investment committee, hey, this is the risk we're assuming, like this is the worst case. We didn't design it, or maybe we did design it to be the absolute worst case, but you can kind of present the relative risk that you're taking from an overbuild perspective based on the use case assumed. And you can prove that you're taking into account these operating characteristics. Maybe you use Storlytics or some other consultant to verify that you assume the correct state of health and depth of discharge. You're not falling below that 65% state of health percentage that Sherif mentioned, because that's at least a typical maybe warranty guardrail that we've seen. If you as long as you don't operate it out of these guardrails, which maybe your model shows, then you're backstopped by that battery warranty. If your model isn't sophisticated enough to take into account those operating characteristics and sort of guardrails that are within your battery warranty, then your pro forma model and IRR is at risk. And then finally, a point, just about layout and design, having that to consider future augmentation strategy. These are all mitigants to having an undersized BESS upfront. So hopefully that kind of answers the question and somewhat kind of ties up what we learned and how we all can kind of be better informed and provide our investors and whoever makes the kind of financial decisions at your company to design optimal battery storage projects.
I'll just add one thing on top of that. Sometimes kind of, as you look to the risks, the mitigation is just don't, right? I've been kind of puzzled by, the number of projects I've seen with, assuming a very smooth DC augmentation throughout. I've seen some strategies assuming we're going to be adding new battery racks every year. This is DC augmentation. We're just adding battery racks year over year over year. So I think that's mainly because most of the times there's not really a technical dive into really how you're going to do things. It's just more of a business review or so. But on our side at Duke Energy, we just recognizing the potential risks with the current DC augmentation strategies, we just made a decision for now to just stick with AC augmentation until we kind of get more comfortable with DC augmentation if the risks go down. But all right, I'll shift to another question by Iman. So which of these two strategies are more appropriate? Charge discharge battery from 30 to 70% state of charge for 100 times, or charge discharge battery from 10 to 90% state of charge for 50 times. And kind of like what Iman did there, if you do the calculation, I think you'll get probably the same number of equivalent cycles there, which is exactly what we did in the first optimization. We did the deep discharges and the shallow discharges, and both of them, it was one cycle a day. And I think what we found with the specific LFP battery model we utilized was that the shallow discharges were less impactful on degradation than the deep discharges. So in this case, if you're using that same battery OAM, you're probably looking at a more economical first case you have here. So going from 30% to 70% state of charge back and forth. Right. And Adam, we thought we had got another question by, oh, you're typing that question. Okay, great. I'll take a couple more here. All right, great analytics. We sure have come a long way since 15 years ago when we started on energy storage in California. Would new energy storage and DERMS, as well as rooftop solar plus storage and EVs, change these analytics? And also any enhancements from AI that may be expected soon? I don't know. that's just too broad of a question to, I'll be frank,
Well,
to provide any kind of a meaningful.
I can maybe put a little color on that, right? So what it would change is if you add new energy storage to the California grid and DERMS and rooftop solar plus storage and EVs, it changes the market dynamics that you would potentially be compensated for. The revenues you would receive being one of those battery participants in the CAISO or California market, right? So I think that's probably the answer to your question. And the way that it changes the analytics is, in this webinar, we made it pretty simple. It was a fixed $15 per kilowatt month toll agreement. So it really didn't matter what happened in the CAISO market. You have that offtake agreement with one utility. But there's, several different players or entities that want to just participate in the merchant market where that revenue stream is going to be very variable and volatile, and it will change as additional energy storage, DERMS, rooftop solar, et cetera, are added to the grid. As far as AI, I think a lot of these trading algorithms that you see that help project owners trade their batteries in those merchant markets, I believe they're using AI technologies. I personally am not by any means an expert in AI, so I couldn't really speak to the details there, but that's probably, I'd probably go to an optimizer or kind of a trading algorithm type entity to probably learn more about that.
All right. Again, Adam, I'm glad you're here. All right, let's take this next one here. What are the key factors to consider when constructing battery usage profiles for various grid services? I guess the highest priority one I'll mention here is just to make sure you're accounting for the entire use case stack. In the beginning of this workshop, Moemen talked about kind of stacking different battery applications and use cases or prioritizing them. So when it comes to degradation, as an engineer, I personally like to be more conservative. So if I think I'm going to be performing 3 use cases, I want to build that into the usage profile I'm developing. And, if I end up using less use cases or doing less of each use case, that's fine. But it's better to kind of overestimate than to underestimate the amount of usage you're forecasting. So yeah, that's one thing I'll mention there. I don't know, Mohamed or Adam, anything to add on that one?
Nah, I think he did pretty good.
All right. Okay. Last one here. Question for the speakers. The average cost of O&M in the US for e.g. 10 megawatt hour, 2.5 megawatt system. How about 80 megawatt hour, 20 megawatt system? Do the numbers change? Oh, so the cost of O&M for different size projects. Are these reports available for balancing market forecasts, in particular for Japan? I don't have no idea about the last one. The first two, yep, O&M costs do vary based on the size of the system. As kind of Adam alluded to in the augmentation case here, you can see he accounted for the additional OPEX of the phases of the projects we're adding. So yes, it does depend on the capacity of the system. One portion of it that definitely depends on the capacity of the system is the cost of the performance guarantee from the battery OEM. For a battery OEM to guarantee your battery system, he's going to obviously charge more for kind of the bigger the system is, basically. But Adam is the expert on finances, so Adam, I'll check with you.
I mean, I don't, I'm not here to necessarily give out cost information, so I apologize if I didn't answer that question earlier. But I'd say there's all kinds of different entities out there that you can get sort of costs from. At least just if you're looking for averages. If you have real projects that you're looking for quotes for, Flexgen's happy to provide a quote. But generally speaking, to answer the question, the costs are going to be very project dependent. It depends on where they are. It depends on what you're doing. It depends on exactly the services that you're looking for. That's probably how I would answer that question.
Oh, perfect. Thanks, Adam. All right, and last one we have here, and I think this one is directed towards Storlytics. So, Moemen, I'll direct this one to you.
Yep.
Yeah. So, will you explain again how this?
Yep. He is asking about the license, how the license works. So basically, we have three current versions of Storlytics. The trial version, which lasts for 14 days, and we have two other versions, the base one and the plus one. What it costs, the base one is $10,000, the purchasing price, and for the plus one is $12,000. What type? Okay, he is asking about the reports we generate. So we have basically two main modules in our software. The first one, the battery profile creator, and we went through that recently in the slide. So it generates one report, and it also supports the output CSV files of the simulation. On the other side, for the battery testing modular, we have it also produces the full analytical report that Sherif went through for optimization 1, the optimization 2, like the charts for the SOH and the battery degradation. And I think the diagram for the losses. So here are the two reports, and I mentioned the output CSV file. Yeah.
All right.
Yeah.
Thanks, Moemen.
Thank you.
Okay, I think that was the last question. So we'll go to this last portion of the workshop here. Now, bringing it all in, what did we learn today, right? Wow, man, a lot of slides to go through. All right, here we go. So I'll just take these point by point. So first one here, the best usage profile heavily affects battery degradation and accordingly project size, right? And we're not talking pennies. That's, we've seen in the first optimization that it made a huge difference on the beginning of life capacity between one cycle with deep discharges and another equivalent cycle with shallow cycles. So now we know that it is consequential. All right, number 2 here, all cycles are not created equal. So Yep, and this is again to the first optimization. We've seen the differences between the two. Number 3, there is no such thing as best battery. There is a best suited battery for each use case. So depending on exactly what you plan to do with the battery, if you're in PJM, if you're in any other ISO or RTO and planning for different services, or if you're in a tolling agreement and you know how many cycles and the type of cycles, you want to use that to find the most suited battery technology for you. And as we saw in optimization 2, the financial difference and the IRR for using the right technology for the use case is in fact very, very significant. All right, the last point, the risks of certain types of augmentation cannot be ignored, right? So in optimization 3, we went through the finances, we calculated, all right, how much we're going to spend on batteries in the beginning and throughout the battery project, if we're doing augmentation, and how does that affect our IRR? But we then talked about the different risks of different architectures. So I guess some developers are more sophisticated than others. Some may have a way to, and Adam, you can kind of correct me on this, but some may have ways to tie risks to and put dollar signs on them and account for that in the financial side of things. I think, if not, then you definitely want to treat those risks as a qualitative factor and really just account for them if you plan to go with any of these augmentation strategies. But
yeah, I mean, at the end of the day, it's all about every investor is different, right? Some investors have conservative capital. They don't want to take any risk. They want to see a toll agreement. They want to see every operational risk they can backstopped by a warranty or guarantee. But that typically is going to drive, returns lower. Versus if you're willing to take risk, maybe it's merchant, maybe it's also you're willing to take the risk to augment later on and hope that the battery use profile isn't the worst case scenario that we showed. And then you may see higher returns later on. So every investor and capital pool is going to be different on the risk, but it's important that you just know and can attempt to quantify them as best possible. And I think this industry still has a ways to go, but we're getting better.
Yep, absolutely. All right, well, I think that kind of brings us to the end of our workshop here. So big thank you to ATA Insights for organizing everything. Big thank you to Storlytics as well for hosting this webinar. So thank you, Moemen, for that. And Christina, I'll just pass it back over to you.
Well, thank you. Thank you so much, Moemen, Sherif, and Adam, for a great session. I think we'll have to take a look a couple of times more and review all the slides, especially to hear Adam's take on the battery joke again. But thank you for such a great specific workshop and answering all the questions that the participants had. That was over, I think, 40 questions or so. So thank you so much. We hope to see everyone very, very soon. Although it was a 4-hour workshop, we cut it to 3. So I think that you guys were very, very effective. But we will share the slides and the recordings in a couple of days. So everyone, thank you so much for attending. And I think that's a wrap up.
Great.
So once again, thank you everyone then. Thank you, Mohamed. Thank you, Sherif, and thank you, Adam, and everyone that is there. I was still like bracing for another hour, to be honest. So we actually stored 1 more hour to do something else. There you go. Good. Thank you. See you later, guys.
Right. Thank you all.
Thank you.
Thank you. Bye.
Bye.